think my computer is acting properly today. So again, I just want to write down the general formula, right? So if we have a function f, that's a function of some variables a, b, and c, then the error in f is equal to, again, remember we add the little partials, the little errors in each of the variables, and we do over quadrature, right? We do the sum of squares. Right? So this is going to be, I'll just write in a different color. So we're going to take the partials of the function, sorry, that's the wrong partial symbol, it's this d, with respect to each of the variables, and we're going to evaluate that derivative at the point that we've measured, right? So we're going to take whatever value of a we measure, which is a bar, and we're going to evaluate the derivative at that point, right? That tells you how much the function is changing as a moves at that point. And we're going to multiply it by the error that we observe for that value and square it. Like that. Remember, so each value has a value that you measure plus or minus an error, right, for each one. Right? So our mean value, right, and your uncertainty, right, which may be a standard deviation if it's normally distributed. Right? There's different instances of what kind of delta do you use. Typically, we use a standard deviation. We'll talk a little bit about that today. And so I just need to add the rest of them, right? So we're going to do it over b now and all the other variables from here on out, right? So we just add over it. Oh, sorry, that's not a square. I apologize. Where b is evaluated at its value times the error in b. Squared plus plus plus. Okay, and we saw that you can use this formula to derive anything you want about if your function is a sum of numbers, right? We looked at that. If it's a product or a quotient of measurements, you get a different formula. The important thing is that remember that we need to make sure that everything that we're comparing on the same scale, right? So we want to make sure that every term in this has the same units as the output. Okay, so the assumption here is that the units of this are the units of f. And that's not too hard to see. We can just kind of do something that will trigger every calculus teacher in the world. But we can just multiply. Imagine this is just a quotient, the change in f divided by the change in a. So these are just variables, right? And here's the change in a, right? We can multiply dA by dA, and we're left with df squared, right? And that's going to have units of df, right? df squared square root gives us df. Right, so it'll have the units. All right, so this is completely general. We don't have to, I kind of screwed it up last time. I put fractional errors here. We don't need to do fractional errors. The only time we need fractional errors is if each of the terms have different units from each other. All right, that's why we remove the units by going to fractional error and compare fractional errors instead. Right, so for multiplication, that's very important because often you're comparing two different numbers that have different units. And so there we want to use fractional units or fractional errors. So let me just write that kind of generally. All error terms, and by error terms I mean one of these orange ones, need to have the same units as the output. Okay, and we're guaranteed to get that as long as we calculate our derivatives properly. Okay. Now, when we did the multiplication rule, right, where we multiplied a by times b divided by x times y, there we had to use fractional errors, right, because everything may have different units, x, y, a, b, they may all be different numbers, different units. So we use fractional errors, but in fact, this derivative, if you do the math out, right, so you take this formula and apply it to a function that's just a product and a quotient of numbers, you'll get the same result. Right? You'll get the fractional error will come out of this equation, and all the units will work out. Okay, so it's just one of those things you just have to double check. Just make sure that when you're comparing things that they're all apples to apples, right? That they all have the same units, or they all have no units at all. Right? Otherwise, you have to use fractional errors. So you would use, instead of df, you would use df over the value of f that you measure with your experiment, right? So in the case of the lab that your guy's doing this week, F here is the moles of the gas, which is a function of the temperature and the volume and the pressure, right? And F bar here is the value of the moles that you calculate for the amount of material in your bulb at the values of the volume, the pressure, and the temperature that you measure, right? The average values. Right? So this is the best, this is your mean value, mean experimental value for the output. Right, and you would want to consider that for the variables as well. So I'll just add that, right? So same for dA over A, et cetera, et cetera. Right? You just want to make sure everything you're comparing is apples to apples. That's the most important part. Right? It doesn't really matter how you display those things as long as everything's consistent. All right, so let's do a little. Let's just do a little really simple and fairly interesting example for this that comes out of my. This is a great book. I posted a chapter of it on Canvas if you're interested on this exact topic. This is a book written by an experimental physicist, John Taylor, out of Cambridge. I think he taught at Berkeley. He's a molecular physicist, atomic physicist like me, and he writes. This book is a beautiful book for undergraduates. It teaches you statistics, everything you would need to know about statistics and uncertainties for a scientist. So it doesn't go through all the BS that the mathematicians care about. It's a very practical book. It's got great solved examples. And I can give you a PDF copy of it if you're interested in the future. I'm actually a little surprised that so many of you are forensic scientists, yet you guys don't get this. Do you guys ever learn this stuff in your class? I think you guys would have to be concerned about uncertainties in things that you measure in an analytical or a crime lab because you want to constrain your values. So I think it's really important to think about these things, and I think they're kind of underappreciated in our literature, in our curriculum. So that's why I like to teach it. So let's just do a really simple problem. All right. Sometimes it's just easy. Some problems are just as easy as just doing a little bit of math. All right. We don't really have to do any derivatives and stuff. If we know uncertainties, say for instance, if you're using a ruler and you know that ruler is good to about 1/16 of an inch, we don't have to do any calculus for that variable. If something's dependent on the length, we don't have to worry about that. We know the uncertainty. It's 1/16 of an inch. It's an absolute uncertainty. So the fractional error is always going to be the same, right? Delta A is going to be 1/16 of an inch if this A is the length. And then your value of A depends on how long you're measuring, right? How long the length is. All right, so let's look at that. Let's just look kind of a really simple example.
I have a quick question.
Yes, ma'am, go ahead.
So like when you're talking about something like a ruler though, to calculate the actual error, like why wouldn't you use things like the triangular uncertainty?
Well, that's a good question. Right. Yeah, that's a good point. So I'm looking at this from a very trying to get a good approximation for the uncertainty in as simple as the way as possible.
Okay.
You're exactly right in the sense that if I measure a length on a ruler, that my uncertainty isn't really the distance between the next ticks, right? So every tick is 1/16 of an inch on a ruler. So if I measure it at, let's say, 1/8 of an inch, I would say naively that my measurement's somewhere between 1/16 and 3/16 of an inch. But in fact, it's less than that because it's a triangular distribution, not an absolute one. And as we learned in the lab, the actual uncertainty is a little smaller than that, right? By about a square root of 2 or something, a square root of 3, I think.
Okay,
right?
Thank you.
So these are estimations, right? And in fact, I'm making some assumptions here, right? There's a really important assumption here that I'm making that I haven't mentioned at all, right? This is only an approximation to the answer, to the actual uncertainty. And the reason why is that I'm assuming that A, B, and C are completely independent of each other, and that if I move A, it doesn't affect the value of B, right? If I move B independently, it doesn't affect the value of C, and so on, right? So there are no derivatives in here that are functions of changes in both two constants, right? A second derivative. Think of a derivative that looks something like this, right? So what if, for instance, there may be another term in here, I'm just going to kind of put it in parentheses, that looks a little bit like the second derivative of the function with respect to two variables times the error in those two variables. Right? And this number, so this is under the square root, of course. Right? This number measures how the function changes as you move the two in a correlated way. Right? So if A affects B and B affects A, this term's going to be non-zero. All right, so what assumption we've made is that all the parameters are completely independent of each other, which is not always true, right? So the real uncertainty is going to also have these second derivative terms, maybe even third derivative terms that are where all they're dependent on each other. Right? You can just keep going down the list, right? And we're just going to neglect those terms. We're going to assume that they're zero, and that gets us pretty close to the right answer. If you're doing very, very precise work, like you're, for instance, a high energy physicist at the Large Hadron Collider and you're looking for the Higgs boson and you're trying to do statistics, you have to start thinking about these things a lot. In fact, that's one of the biggest challenges with doing high energy physics experiments is not the experiment's hard and expensive, but the statistical analysis of the results is just as hard. And in fact, that's one of the things that enabled the LHC, not just the engineering itself, but also the software and the statistical analysis just to model the damn thing and get a statistical measurement of whether we actually see the Higgs boson or not. That challenge took 10 or 15 years just to start thinking about how do we estimate these terms in physics. So we're just going to ignore these, right? We're not going to worry about these things at all. So again, everything here is we're just trying to estimate, okay? And the fact of the matter is for most things, this gets us close enough. Close enough. Okay. Hope that answers your question, Monica.
Yeah, thank you.
All right, so let's do a fun example that I pulled out of the book. I'm going to set up the problem for you, and then we're going to think about how we evaluate the error for this. Okay, so the problem is very simple. I'm going to have a motor here. All right, this is an electric motor. Think like literally a motor from well, I was going to say from a Tesla, but it's not the same. So this is an electric motor. All right, and this electric motor has a turbine or a little wheel thing that spins. All right, so the motor drives this shaft, and this shaft is connected to a pulley. All right, so this is a pulley that has a wire, a rope on it that is attached to a mass that's hanging of mass m. All right, classic physics problem. All right, and so I'm going to drive the motor, and there's a differential in here to couple the rotational motion in here to rotational motion in the pulley, and I want to lift the mass up. All right, so the goal here is to lift the mass from an initial height to some new height h. Well, maybe not that high. That's above the above the pulley, but you get the idea, right? I want to think about a motor, an electric motor, driving this pulley to lift this mass by height h. Okay, and this is what's called a DC electric motor. It's a direct current, not an alternating current. All right, so you just feed a voltage into it and it runs. So there is sticking out of it, the power source, if you will, is just a wire that's connected, well, to a transformer. But there's a plug here. There's my plug. All right, and that wire is driving electricity. Right, we'll call it driving an electric field to drive this motor. Okay, and the question I want to ask. All right, so I have this set up. Right, and I can measure, right, how much energy it takes to raise the mass by h, right? I just measure it. I measure how long the motor runs, at what voltage it runs at, what current it runs, and I can calculate the energy or the power. Okay, so I can figure out how much energy it takes to do this. But what I'm curious about is the efficiency. So for every joule that the wire supplies to my motor, how much of that 1 joule is actually being used for the work, right? The lifting work. How much of it is actually used for something useful and how much is thrown away? Right? This is a classic question in chemical engineering and also in mechanical engineering is how efficient is your machine? Right? So we can define the efficiency of any machine from a thermodynamic perspective. call this E. Right? And that's going to be basically the work that's done by the motor, right? The energy used for the actual purpose. So gravitational work or whatever you want to do. We'll just go work done. And we want to think about how much of the total energy created by the motor is used for that, right? So the denominator is going to be the total energy delivered. Okay. All right. So I want to calculate this, but what I really care about actually is again, it's not hard to do this calculation. We just need a way to measure voltage and a way to measure height and a scale, and we can figure this problem out. But the question is the uncertainty in that number. And for motors, efficiency is extremely important. In fact, in some ways, it's the most important metric other than the power that a motor creates. It's the efficiency of that motor. And a really good example of that is combustion. All right, so like a normal internal combustion engine. Does anyone know off the top of their head how efficient those engines typically are in terms of percentage? Does anyone know? How about someone wager a guess? Yeah, go ahead. 70%. So what Sydney's saying is that for every joule that gasoline creates, 70% of it is used to drive the wheels. I'll tell you, if Sydney creates a combustion engine that's 70% efficient, he will change the face of this earth, because there is no combustion engine that efficient. In fact, the typical combustion engine, and I did a quick calculation for my car. I have a turbocharged Honda. Turbocharged cars tend to be very efficient compared to non-turbocharged cars. The efficiency of my car is about 35 or 36%. All right, so it throws away 2/3 of its energy to heat or friction, right? Or for instance, to the air conditioner, right? Or the radio, right? Some of it's used for electrical power, but in terms of driving the wheels, it only is about 35% efficient. In fact, I went to a talk when I was at Argonne, given by a Korean engineer from Hyundai. We were really big into combustion at that lab. And he was talking about new developments in engine technology at Hyundai, and they had a big party and they were really, really celebrating because they made a new engine for their hybrid cars, their hybrid technology, a combustion engine, that was 51% efficient. And that was revolutionary because the best they could do up until then was about 49, and they wanted to get over that 50% hump. And they're finally starting to do that in small displacement turbocharged engines in hybrid cars, which is why that's all you see now are cars with, like my car, the engine's only 1.5 liters. It's got less, the reactor inside of that is smaller than a pop bottle, a Coke bottle, if you will. It's a tiny, tiny engine, but they make them extremely efficient so that you generate as much power as possible out of that small engine. Now you can compare that, for instance, to, I'm gonna stop talking about it now, but you compare that to an old Chevy, right, from the 60s, like something your dad drove or something like that, like a Chevy Nova, which had what, like a 6-liter V8, just a massive engine. Those engines were maybe 15 or 20% efficient. They threw away all their energy. So we've made a lot of big strides in that regard, but you really can't do better than 50% for combustion. Now for electric motors, you have a better luxury. Electric motors tend to be very efficient. The only thing that slows electric motors down are friction. So you don't really have heat loss from electric motor other than through friction. Okay, so let's look at the efficiency of this, right? And so the work done, again, I'm just going back to old school physics. This is a gravitational potential energy problem. You're raising something by height h, and it's fighting against the force of gravity. And the energy of that motion is the opposite of the gravitational potential energy, which is mgh. Right? What's g? What's the acceleration due to gravity on Earth? Yeah, you guys know that number. That's one constant we know. We know this is 9.81 meters per second squared. Did you guys know that this actually varies depending on where you are on Earth?
Yeah, that's great.
Yeah, it varies anywhere from about 2 or 3%. So there are places where the gravity is higher than others. I'll try to find a map of it. It's really cool. All right, so you have mgh, and at the bottom, it turns out that in a DC engine, the total energy that's given to the motor is based on the voltage of the motor times the current, I, that's supplied, times the time the engine runs to lift it. All right, so this is the time the engine's on. I is the current of the motor, or of the energy source. So if it's coming from your wall, it's typically about 15 amps. And the voltage of the motor. All right, it's just electrical work, EIT. Okay, so in order to figure out the efficiency or to measure this, we have to bring out a couple of gauges, right? We need a scale, we need a ruler, and we need a multimeter, right? A multimeter is something that measures voltage and current. Never seen a multimeter, you will in this class in the next rotation. And then we also need a stopwatch. Right? Okay, and so typically, so what I'm going to do is instead of thinking too much about the exact numbers here, let's just think about uncertainties of scales and multimeters and things like that in terms of a fractional uncertainty, right? Can we make an assumption about roughly in terms of a percentage how much the error is relative to the value? So let's just say very generally that the fractional uncertainty or fractional error for the things that we can measure easily, M, H, V, and I, is about 1%. All right, or percent error. I shouldn't call that fractional, but right, we could also call this, right, fractional error would be 0.01. Right? Okay, and let's say, for instance, we use one of my really cheap, shitty Chinese watches to do the time, and so my fractional error in time is a little high. Right, and we'll say it's 5%. Now, in reality, it's probably going to be a little bit lower, but let's say I have a really bad watch that I spent $20 on, and it doesn't work very well. All right, and so now what I want to do, so now I have fractional errors in all my values. Right, so what now is the fractional error in the efficiency? Right, and we're going to do it two different ways. And I think this maybe helps talk about how we make approximations to error. And again, there's no right or wrong way to make approximations about error. As you saw, when we went to quadrature, and as I talked about just now, we make approximations there, right? So we're already just approximating things. So it's not the exact error, but it's going to be a useful guess, right? And sometimes that's all we need. It's just a good sense of where the value may be. Right, so let's just think of the naive rule that we talked about where we just add the uncertainties. Right, no quadrature. Right, so let's try this, the addition rule. Right, where we're going to say that the fractional error in the efficiency, right, which is the error in the efficiency divided by the absolute value that you measure for the efficiency for your system, is equal to just the sums of all the fractional errors. Right, so we're going to have this equal to dm over m plus dh over h plus dv over v plus di over I plus dt over t. All right, we're just going to add them up. Right? That maybe is a reasonable way to do it. Right? We saw that, as we're going to see, this is the worst case scenario for the error, and I'll explain why. Right, so how do we calculate this? Well, we already have the numbers for all of these, right? This is the fractional error in m. It's 0.01. Right? We could just substitute them all in, right? Until we get to t where it's 0.05. Right? So these numbers are just these fractional errors. Right? So the really easy thing we can do, right, is just say, well, let's see. We have one this is 0.01, 0.01, 0.01, 0.01, and this is 0.05. Right, so let's just add them up. That's 9. Right, we have 4 ones and a 5. That's 0.09. Right, and this would say that our percent error or our percent uncertainty in our efficiency is 9%. Right, really easy. Right, just add them up. But what we're going to find is this number is overestimating the error significantly. Okay. And I want to explain subtly the differences between adding in quadrature and just adding straight through and what they each represent. All right, so in quadrature, addition, we have that delta E over E is equal to the square roots of each of the fractional errors, right? So it's going to be, I'm not going to write them out, but it's going to be 0.01 squared plus 0.01 squared plus 0.01 squared plus 0.01 squared plus 0.05 squared. Okay, so I'm taking the sum of the squares. I'm taking the square root, right? Think of it as like a hypotenuse of a 1, 2, 3, 4, 5-dimensional triangle. And so once you calculate that again, I'm not going to, we can just do that on a calculator. You find that this is 0.05, sorry, 0.05, or 5% uncertainty, roughly. Okay, so when we just add the errors together, we get 9%. And then when we think about things more from a geometric point of view, right, where we think about things in quadrature, think about these as vectors, if you will, and you're adding all the vectors together and calculating the length of the total vector, which is just this calculation here, you get 5% instead, right? So it's about factor 2 smaller. All right, so what statistically is the difference between these two approximations? Okay, why is one better than the other? The answer is no. It's just a matter of perspective. The fact of the matter is that I would call this a more accurate depiction of the energy, or sorry, the error in your efficiency. This is more of a worst case, right? Worst case scenario. And let me explain what I mean by that. Imagine that I'm measuring M, H, V, I, and T, okay? And there's an actual value, right? The correct value for each of those. Like if I was able to measure it perfectly, okay? So think of that, that's a M bar, H bar, V bar, right? You've measured them very perfectly. But the actual value for these is slightly different. Okay, so imagine that when you measure T, I, V, and H, and M, maybe this is a good way to write it. Let me show you how this works. So let's say, for instance, it's probably easier to draw this. All right, so let's imagine you make a bunch of measurements of a variable. Okay, let's do M, for instance, right? You measure M. So this is the value of M that you measure. Okay, and we're going to measure it. We're going to make what's called a histogram, right? We're going to, on the y-axis, for every measure of M that we make, we're going to measure the counts of how many times we measure it. All right, we call that a histogram. So let's say, for instance, we have a correct value for the mass. Now imagine we have a maestro, a chemistry maestro who can measure all masses precisely. And he says the real mass is here for that mass. And then you go and measure the mass yourself, right? And so maybe you'll end up measuring the mass over here, maybe you'll end up measuring it over here, but there's going to be some distribution to the number of measurements of each measurement as you do hundreds of them, right? You're going to have a distribution, right? So you might find some, so when you go measure, you might find, occasionally you'll find some values right in the middle, right? And then occasionally maybe you'll find some values on the edges. All right, if you guys did that balance, the triple beam balance in lab, you've got a fairly large distribution of errors on the masses. Right? And so you can say that if we take an infinite number of measurements, that we have a distribution of values that looks like this. Right, so this is the number of measurements on the y-axis. Okay, and so ideally, if you make a really, really good measurement of M, you'll fall right here, right? This is what you want to calculate, right? You want to do a bunch of measurements, and then you'll find this mean value right here, and that's what your measurement is. But imagine that when you make that measurement, you don't do it very well, and instead you find yourself on the edge. Right, so what if you go in and measure this instead? M measure. Okay? And so what that means is that your measurements are probable. I mean, they can happen, right? It's within the accepted distribution of values that you can get for your measurement within the uncertainty, but you're on the edge of the distribution, right? You have some sort of bias, or you're just not very good at measuring things, and so you end up having a lot of systematic error in your measurement abilities, in your procedure. And so your measurements for M or any of the variables kind of show at the edge instead of you're getting the actual middle, right? Okay? So you have some bias there, right? And so what this says, so when you do the straight additions, what this is saying is it's approximating what this is saying is that it's approximating the error and the efficiency given that your measurements of each of the variables, the experimental variables, are on the edges of the possible distribution. All right, that you've done kind of a crappy job in your measurements and you're off by the real value from the mean value a little bit, the real value for each variable. And so this is like the worst case, right? This is assuming that you're kind of sitting on the edge, your measurements are sitting on the edge of the probable values for each of them. Okay, so this is a worst case scenario. It's a very conservative estimate, which assumes that you are screwing up and your actual measurements are biased in a slight way statistically relative to the actual value. So in quadrature is the true average. So in quadrature, you're making the assumption that your measurements, that the mean of the measurements you make is right in the middle. Okay, so when we're assuming that we're kind of on the edge, we can add, and this tells us something about the uncertainty when our measurements might not be right at the mean. But let's say you're really good at your procedure and you measure a bunch of times, you correct for all your problems, and the mean value that you measure is right in the middle of the distribution of probable values, then the uncertainty is the quadrature version. Okay, so the quadrature addition is in some ways the mean expected error. All right, it's the average of the expected error. All right, so this is in some ways, it's not the best we can do, it's not the worst we can do, but it's the average that we can do in our measurement. All right, so this is what I would call a mean error, a mean absolute error. All right, some people call it in science a mean absolute deviation, or a MAD. That's another term for it. Right? And it's just saying that on average, your uncertainty, if everything is averaged out, all your errors and your biases are all averaged out, that your uncertainty is going to be around 5%. Okay, does that make sense to everybody? Yeah, go ahead, Monica.
Wouldn't you multiply by the denominator, so the error, the actual?
Yes. So again, this is not a quant. This is a quotient of two numbers. So this is the fractional error, 0.05.
But to get the actual error.
But if you multiply both sides by the value, it would say that your error is 0.05 of the value.
Okay.
So if E is, let's say if E is 50.
That makes sense.
Then your error is plus or minus 1. Or something like that. I can't do math, sorry. Yeah. But you get the idea, right? So this is not a monolithic quantity. This is the error divided by the value. So you can use algebra on it, right? So, of course.
So also I have another question. So
yes.
like using I understand like how if you're assuming that it's like on the edge, but like in what case scenario would that happen? I guess like why would you ever use that?
Well, it's when you right. So the assumption we're actually making here that eventually if you make enough measurements, you'll get this mean correctly. That's the central limit theorem, right?
Yeah.
It says that eventually the mean of your sample reaches the mean of the population, which means if you take infinite measurements, you'll get to recreate this distribution. So what this is saying is that you have some error because your sample isn't exactly the same as your population. You have some bias.
Okay.
And what it means is that what it's expecting is that your value that you measure is going to end up going to be at the standard deviation of the distribution. So let me draw that. So if your uncertainty in M if delta M is the length of this whole orange line, right? So this is delta M. this whole length line, the assumption when you do the additions is that all of your measurements are at the standard deviation of the population.
Yeah, that makes sense.
Okay, not the mean. All right, so the addition is assuming that you're always at the edge, right? It's the worst case probable scenario. And this assumes that you're actually making a proper measurement and that your sampling is unbiased, and you end up measuring the mean on average in your sample. Does that make sense?
Yeah.
Okay, cool. All right, so in general, using quadrature is the right choice. Okay, unless you really think you're garbage, then adding might be a reasonable thing to do. But in general, we just do quadrature because we just take means of everything. Okay, it's just easier just to do means and standard deviations. Right? Everyone understands that. Any questions? Any more questions about this? All right, I'm going to put some practice on this on the next homework. Just a few kind of easy problems. Maybe I might add another kind of linear regression problem where you can do some error on uncertainty of linear regression. It's just some easy practice on that. Okay. That's all I want to say right now about uncertainties. I think this week's lab and last week's lab will kind of fill in the gaps, and if we feel like we need to talk a little bit more about it, I'm more than happy to. And again, as you can see, I change my lecture schedule based on your needs. So if we feel like we're uncomfortable about something, I'll make sure to spend more time on it. Okay, so what I want to do now for the rest of the class is to now start transitioning back into thermodynamics. And I want to, it's a little bit of a segue, but I want to talk about entropy a little bit more. And it's a kind of our conceptual discussion of problem 4. All right, problem 4 I set up so that you can kind of solve it on your own. But I really want to talk about the nitty-gritty details of the subtleties of that problem, now that you've been slowly introduced to the idea. So let me get my notes. So I want to talk about statistics today and how thermodynamics, entropy and all that junk, is a statistical theory. When we measure energy, we measure, and later we'll talk about enthalpy and Gibbs and all of that, all those things you know and maybe love or maybe hate. These are all statistical parameters. They're statistical things. They're averages that we take. All right? It's not an exact value. In fact, what we're going to see is that if you measure an ideal gas at a given temperature, you'll get an average energy and a standard deviation, but you don't actually know the exact energy, right? Because everything's random, and we'll see that today. All right, now I want to set up the problem. And this is a really beautiful result from a man named Ludwig Boltzmann. I'll have to show you, maybe next time I'll show you his headstone at his gravesite. It's really cool. Very famous and nutty German physicist. Many of the famous thermodynamicists in the world over history committed suicide. That seems to be the way that statistical physicists like to end their lives, is suicide. And so maybe that says something about this material. I'm not sure. So hopefully no one here feels that way about thermodynamics. So what I want to do today is I want to derive a statistical representation of entropy. Right? Entropy ultimately is the thing that we really don't understand, right? Because it's kind of the average of all these motions we can't observe, right? They don't contribute to the work of the system. It's all this junk that just gets jumbled up into the entropy. So I want to tackle it in a statistical way. All right, and we're going to learn really interesting insights about entropy by tackling it statistically. All right, so let's set up the problem. We're going to go back to boxes again, but we're going to do this a little differently. Okay, so inside, I'm going to have this big box, and inside of the box is a little sub-box. All right, and the interface between these two boxes is closed. All right, so you have some thermal insulation here. I'm just going to kind of color it in. All right, so this is a closed. This is thermal insulation. All right, so nothing can leave. No energy can leave this outside area. Okay, so we have like a nice little layer, protective layer, and inside of this box, I'm going to draw a bunch of smaller boxes. All right, I'm just going to draw a couple. We can draw as many as you want. It doesn't matter. The number is irrelevant. I'm just going to draw a couple. You can draw 4. You can draw 10. Doesn't matter. The answer is irrelevant. The number doesn't matter. All right, and each of these boxes, all right, in between the boxes is a material that allows heat to transfer, a diathermal material. So no energy can escape here, but energy can transfer between each of the boxes, the little sub-boxes, okay? So this is a conductive material. Oops, sorry. So the interior, maybe I'll just draw it blue for water. Maybe you can think of it as a water bath or some sort of material like Teflon or wool, something that transmits heat effectively. All right, so we'll call this instead, right, this is going to be a isothermal bath. All right, so it's fixed to some temperature. Okay, and energy inside of each of these boxes is allowed to transfer. I'm just going to color them in just to make it pretty. All right, and we can number these boxes. Okay, so we'll just arbitrarily, we'll say this is box 1, box 2, and we'll just randomly pick one, and we'll say this is box J. Okay, so there are some number of boxes in there that are allowed to change. All right, each of these boxes are at thermal equilibrium. Okay, so each box has a volume, a number of molecules, and an energy. All right, so the initial state, initially, each box is initialized such that is ST. The energy, so let me use the label that I used before. Sorry, the total energy of a given box, U sub J, is a function of the number of particles in box J and the volume of the box. And also, sorry, yeah, right. So the energy is determined by the number of particles in the box and the volume. Remember, the temperature is fixed. Okay, so we don't have to worry about temperature here. So we have the number of particles, and each one has a volume. Okay, and then what we're going to allow this to do is we're going to allow the energy to move through all of these boxes and distribute itself. All right, and what I want to ask now is, what is the probability that I pick one of these boxes out and its energy is a specific value? Okay, so what is the probability that a given box has energy E? Any value you want. Okay, so we're allowing energy to move around and equilibrate, right? So the question I want to ask, so then let me just do this. So we're going to equilibrate. Right? And then the question is, what I want to ask is, what's the probability that I observe box J, or any box, at some energy E sub J? All right, any number I want. Okay, so let's do a little bit of notation. Let's set up the math for this problem. And we're going to see that the math is actually pretty straightforward, and we're going to have a really interesting result from it. Let's say that the number of systems, so the number of boxes, with energy U sub j or E sub j, however you want to write it. Right, is equal to, the number we're going to call that is A sub j. All right, so we want to ask the question, we're going to go look and measure the energy of each box after it equilibrates to the temperature, and ask the question, what's the probability, or how many of the boxes that are a specific energy that we want to measure? All right. So some boxes might be lower in energy, some might be higher, they're all equilibrating and fluctuating. All right, so some of the there might be one box, there might be 100 boxes at that energy, we don't know. Okay, but let's just think about that for now. There's some way to count the number of boxes of that energy. And then let's say also that the total number of boxes is just the label fancy A. Okay, total number of boxes is A. Okay, so it's going to be hard to measure this necessarily, but we can do a comparison. Right, so the question may be is, what is the ratio of boxes that have one energy versus the boxes that have a different energy? Right, so what if we want to think about not necessarily a formula for A sub j, but rather what are the properties, the mathematical properties of the ratio of these numbers? I remember we measure things in differences, relative, so we should take ratios. Absolutes can be very difficult to measure, but relative things can be very easy to measure, of, say, A sub j divided by A sub k for different j and k. J not equal to k. Okay, so we have two different energies, and we want to say, well, how many more boxes have energy j versus energy k? Okay. So maybe energy k is 0, right? We want to see how many boxes have energy relative to the number of boxes that don't have any energy in them. Okay. Maybe something like that, right? And so let's just kind of think about that a little bit, right? So the only thing that this is going to depend on, right? N and V aren't changing, right? So this ratio has nothing to do with the number of particles in each box or the volume of each box. Because the system is equilibrated, N and V aren't changing, right? The only thing that's moving is heat, right? There's no exchange of material, there's no volume change, it's isothermal, it's just heat exchange. So this ratio must only depend on the energies, the relative energies of the two boxes, right? It doesn't depend on anything else because nothing else is changing in the system. Therefore, this must be a function of the things that are changing, which are the energies. Okay, so we can make a claim that this ratio is equal to some function. We don't know what it looks like, but it's some function of the energy of box J and the energy of box K. Right? Some function. We'll figure out that function in a second. Some function. Okay? Well, we can actually make a simplification to this, right? Because if we know, we can set, for instance, a reference value for our energy if we relate everything to 0. Right? We have 0 energy, we define 0 energy, and all of these are relative to 0. Then this function really isn't necessarily a function of the two energies separately, but rather just the relative energy. Right? Remember, energy is a state function. It only depends on the end and the initial point. So that means that this function really isn't dependent on each of these independently, and that Ej and Ek appear in different parts of the function, but rather it's only dependent on the difference of the two, right? The relative energy. Right? So we can actually simplify this a little bit and say that the function that determines these probabilities must be a function of the difference of the energies. That's just the nature of energy, right? We always can measure things relative to each other, so let's just do it relative to the energy difference between the two states. Right? And that's something that we can, for instance, we can measure with spectroscopy. If these were atomic boxes or molecule boxes, we can measure these energy differences through spectroscopy. All right. Now, I know this doesn't seem all that interesting, but it's going to end up very interesting in just a second. We're just going to apply a very interesting guess, if you will. It's not really a guess, just a little bit of logic. So let's go ahead and write that. So let's say, let's just pick boxes 1, 2, and 3, right? And we can say that the number of sorry, not boxes. Let's say energies 1, 2, and 3. Right? 3 different options for the energy. We could say that the number of boxes with energy 2 divided by the number of boxes with energy 1 is just this function that's the difference of the energies. And we can say that about box 3. Right? We can say that the box 3, the ratio of boxes at energy 3 versus the number of boxes at energy 1 is also just the difference of the two. And we can write it for the other case as well. Again, I'm just being very explicit here that this ratio between energies 3 and 2, the boxes of energy 3 versus the boxes of energy 2, is also a function of their energy difference. Okay, but we're just comparing ratios of 3 different boxes, or 3 different counts, if you will, right? These are just the counts of the number of boxes with that given energy. Right? So we have these ratios. We can relate the ratios to each other. Right? So we can just write, just through distribution, the distribution law, just a little bit of algebra, we can always write that A3 over A1 is equal to A2 over A1 times A3 over A2. Right? This is a nice thing to do if we can always connect the probability of seeing one energy, or the boxes of one energy, to the boxes of another one by just kind of leapfrogging our way through the energies. Right? If I can measure A1 to A2 and then A2 to A3, I can now measure A1 to A3. Okay, so I can kind of leapfrog through the energies in this function and determine a relationship between the probabilities. And what this says, therefore, let's just plug in the functions now. Right? This says that f of, let's say, E1 minus E3 is equal to f of E1 minus E2 times f of E2 minus E3. Okay, so what this means is that I need a function that when I go between 2 different steps, right, there's an E2 in the middle, that the function is the same function of the intermediate steps. Right? So if we're going E1 to E3, I got to go E1, E2, E3. So this function satisfies the property that going from that the function for this energy difference is the product of the intermediate energy differences. In other words, not too hard to think about this with a little bit of algebra, I need a function that when I take 2 values, I sum the values, that I get the product of the function evaluated at each of the values. All right, so what this means is that the statistics of thermodynamics, right, if I want to measure probabilities of how the energy distributes in all my little boxes, it's always represented by a function that when I take a sum of arguments in the function, that it ends up being a product of the functions evaluated at each of the arguments. There's only one function in the world that satisfies this expression. Does anyone know what it is? So when you take that function to x plus y, you get that function of x times that function of y. Does anyone know a function that does this? You've seen it before. Go ahead. Logarithms is almost there.
Natural log, I guess.
Logarithms are almost there because, not quite, that would be f of x times y is equal to f of x plus f of y. Okay? You're close though. What's the opposite of a logarithm? An exponential function. E to the x plus y is equal to e to the x times e to the y, right? So this function, by definition, there's only one option here, is that f of x is e to some value, some constant. We have to figure out what that constant is, a proportionality constant, beta times x. All right, so it's a number times x. All right, I have to include the proportionality constant because I can multiply x and y by a value, some number, right? I can make 2x plus 2y, and that's going to be f of 2x plus f of 2y. So I have to have a proportionality constant in here just to make things equal. So what this says is that we can determine anything about the statistics of the energies of this thermodynamic system by measuring this strange exponential function that is a function of the energies. Okay? So this exponential has something, right? If you take x to be e2 minus e3, it says something that the probability, or the ratio of probabilities, is equal to an exponent of the energy difference. Right? Let me write that down for you.
Can you explain again how you got from like the green to the yellow at the end?
Here?
Yeah.
So you understand how I got from here to here? Okay. So, think of, you need to add two terms of e. So think of e1 minus e3 as e1 minus e2 plus e3 minus e2. And let x be e1 minus e2 and y be e3 minus e2. So this is f of x plus f of y. So this is f of x plus y equals f of x plus f of y times f of y. So there's inside of here, let me just write it out. Thank you. This you can think of as e1 minus e2 plus e2 minus e3. You see how the e2's cancel out there?
Yeah.
And these are just the arguments in the right hand side. Okay.
Thank you.
Yeah. Just a little step in. So there's something magical, something exponential in our statistics that we have to think about a little bit. And this is, in some ways, this is the fundamental result of thermodynamics. We're not quite the thermo yet, but in some ways, this statistical distribution, this function, if you will, determines everything about the energies. Right? Just a simple exponential. So let's go ahead and let me just, is it okay if I go next page? Are we all good so far? Okay. All right, so let's go back. So we have that basically for the number of particles in energy J divided by the number of particles in energy K, or the number of boxes, sorry, is equal to E to the beta, we haven't determined what beta is yet, times the energy difference between those two states. So EJ minus EK. Okay, and it's not too hard to go to the next step. Just a little bit of algebra. You can determine that if you let, for instance, AK be 1 and you're doing everything relative to 1, imagine you set the AK to be the number of boxes at energy 0, and you just say that there's exactly one box, or maybe 100 boxes. What's the relative fraction of ones at higher energy? You can write, therefore, that AJ, just a little bit of math, by setting EK to 0 or EJ to 0, you can write that the AJ is equal to E to the minus beta times the energy of J. All right, and it needs a constant. So there is a constant on the outside that we have to determine. All right, so this is an undetermined constant, a proportionality constant. which allows us to relate two boxes together. And let's look at this little beta here. All right, we can kind of start thinking about what beta looks like. So one of the things that we need to have here is that this whole thing needs to be unitless, right? Because this is a number, right? This is a count. Right? This is the number of boxes with energy J. So it's just a number. It doesn't have a unit, right? So this entire thing needs to be unitless. Not only that, you can't take an exponent to a unit. So this entire product here needs to be unitless. All right, so beta has to have units of inverse energy. So in order for this to be valid, the only thing that is allowed is that beta has units. So remember I said that units have these little brackets here. Has units of 1 over energy. Okay, so beta has some magical, what did you say, some connection to the energy, some proportionality constant that gives us something that says something about the energy. Okay, we'll figure out what these numbers are very quickly. So I don't really have the ability at the moment to derive exactly what beta is, but there's a way to derive it. And what you find is that beta is, so what we're going to do is we're going to equilibrate this to a temperature. Right? So what we can say now so at thermal equilibrium, at temperature T, okay, temperature T, we can show very easily, and this is one of the most important parts of thermodynamics, is that beta is equal to 1 over temperature times a proportionality constant called Kb, Boltzmann's constant. Right, so beta is 1 over Kt, which means that the probability of finding a particle in this box that's equilibrated to a given temperature is equal to some constant times e to the minus the energy of the box divided by this constant Kb times temperature. Okay, and you've seen this Boltzmann constant before. I gave it to you in the problem set, but you've seen it in other contexts as well. This is in fact, this is probably one of the more important numbers in this class. I just want to get the exact number. It's defined exactly by the SI units. By the SI units convention, this is an exactly defined number. So this is what's called Boltzmann's constant, Kb. Right, and the value of it is exactly defined as 1.380649 times 10 to the minus 23 joules per Kelvin. Okay, you've seen this number before, but in a different context. If I multiply this number by Avogadro's number, let's do that let's do it really quickly. So if I multiply Boltzmann's constant by Avogadro's number, I have, again, 1.380, I'll just write it out, 1.380 ... times 10 to the minus 23 joules per Kelvin times Avogadro's number, which is 6.0223 times 10 to the 23, and the units are per mole, or minus 1. You get a very familiar number, 8.3145 joules per mole per Kelvin. What is this number? R, gas constant. So Boltzmann's constant is the per atom or per particle gas constant. What is the gas constant? Well, let's just look at the units, right? It has the output of it, right? We multiply it by T, right? We always have, right? It's always RT, right? Pivnert. Here we have KT, right? So T always has Kelvin, right? And it says for every degree temperature, the system is provided 8.3145 joules per mole. All right, so what we're going to see in just a minute is that this is representative of the amount of energy, thermal energy or entropy, if you will, that's provided to the system when you equilibrate it at a given temperature. So it says every time you kick the temperature up by 1 Kelvin and you re-equilibrate the system to that temperature, the system gets an additional 8.3145 joules of energy from that thermal energy. All right, so a relationship that converts between mechanical energy, chemical energy joules, and temperature. It's how we interconvert temperature and energy, Boltzmann's constant or gas constant. All right, so it gives you a sense again of how much energy content there is in temperature, thermal temperature. I'll write that down. All right, so Boltzmann's constant, the gas constant, describes the average amount, everything's averaged, of thermal energy provided by thermalizing your system or your gas at temperature T. Okay? This number is determined experimentally. There's no derivation for KB, right? Just like the speed of light. It just is. Right? And Boltzmann determined this number to actually fairly good accuracy in the 1800s. Actually did a really good job of it. It's really quite amazing how good his theory worked. I think he got it to like this digit. Maybe he had 3 significant digits in the 1860s. He was doing pretty good. All right. This number is now defined exactly. It has no uncertainty to it. It's an exact constant, just like the speed of light. Right? It's one of the fundamental constants of the universe. Right? It's the definition, if you will, of temperature as an energy source. It tells you exactly how much energy is provided by a thermal bath at a given temperature. And it's contributed on a per molecule basis. Right? Each molecule or each mole gets exactly 8.3 joules per unit temperature. Questions? Okay. So we've determined one of the constants, right? KBT, right? So it says that the, right? What does that say? Well, it says that the number of particles, or the number of boxes at a given energy in your thermally equilibrated system is proportional to e to the minus that energy divided by KT. All right? We'll look at that graphically in just a second. Oh, we only have 3 minutes left. Damn, I've been going, this is going fast. All right, so let's actually look at this really quickly, and then on Monday we'll finish this up. So what does that say? All right, so let's think about that, right? So let's do a plot, if you will, of energy. Right? You have a box at some temperature, and we want to plot the number of particles at that given energy. All right, and we may make a choice about how we want the energy to be distributed. Maybe it's continuous. You can take any value. Or maybe it's discrete. The energy can only take certain values. Right? But what it says is that this relationship, so let's think about it. E to the 0, e to the minus 0 over KT is e to the minus 0, which is 1. So the vertical intercept of this equation is 1. Right? And it goes exponentially from there. Right? So if we pick a point here, E sub j, then the value of this is the probability, right? This is the ratio of E sub j, the number of, sorry, take that back. It's the number of boxes with energy j, or the number actually the number of molecules of energy J in a box, divided by the number of molecules of 0 energy. All right, so what happens as temperature increases? All right, so let's just say this is 298 Kelvin, right? So let's say, for instance, this is at room temperature. All right, so what happens if I raise the temperatures, let's say, to 500? All right, so if I raise the temperature to 500, the denominator of the exponent gets larger. So as a function of E, this number is smaller than it is for lower t, right? So if this is a 200, you have some ratio, but if you make it 500, right, that ratio gets roughly 2.5 times smaller. So for an equivalent energy at a higher temperature, this exponent will be smaller. E to a smaller number minus a smaller number is going to be larger than e to the minus a bigger number. Right? So what that means is that t increases, this function decays more slowly. So as we increase the energy, or the temperature, I'm going to clean up this plot just a bit. I'll rewrite everything just to have some space. So this is 298 Kelvin. And this point right here is AJ over A naught. And now as I increase the temperature, right, the function still starts at 1, right, because e to the 0 is 1. But the function decays more slowly because the exponent is smaller as a function of e. So this equation will decay more slowly. So this is at 600 Kelvin. Okay, and then we ask the same question, what's the probability that the system is at E sub j? As you can see, there are now, at higher temperature, there are more boxes at 600 Kelvin, more boxes at E sub j at 600 Kelvin than there are 298. Okay, so what that means is that as temperature increases, more and more, the boxes have more and more probability to exist at higher energies. But it's entirely random, right? This is entirely random. So the boxes randomly distribute the energy around, everything's moving randomly. And the temperature measures basically the occupancy of those boxes and how much energy they can carry. And so if you're very cold, the boxes can only hold a very small amount of energy. Once you get to a very high amount of energy, there's a very low probability of seeing a box with that energy. But as I raise the temperature, the probability increases for a given energy, because there's more energy to distribute. Okay? And the most important thing is that this goes to 0. So what that means is that in a thermally equilibrated box, even at 1,000 Kelvin, if you have enough boxes, there's a probability you might see a box with energy 10 million. Or the box itself, all the molecules are flying like crazy and way out here. There's a non-zero probability of that. So what thermodynamics actually is not at a given temperature, not everything's at the same energy, but rather they have a statistical distribution of energies that's determined by the temperature and this equation right here, this exponential equation. All right, so next class we'll come back to this exponential equation. We'll use it and we'll be able to derive entropy from first principles. All right, this measurement, how this changes the temperature will determine entropy.
Can I ask you a question?
Yes,
I'll let you
ma'am.
pack up those since I know.
Let me just save this and you can ask me your question. Sorry I ran late.